Hey, so today I'm going to do a control test on this robot I've been working on for quite a while. So this robot's a pendulum bot, and what that means is the idea is that it's going to try and balance itself in an upright position. So this pendulum, and there's a few challenges with doing that. But today I'm just going to show you some really basic proportional control that I've been working on for quite a while. The robot's based off a BeagleBone Blue, which is basically a little Linux computer with a bunch of robotic outputs. It's got a IMU on it, so it gets gyroscopic, accelerometer, and magnetometer sampling from that. And because it runs off Linux and it's kind of from the open source community, there's a lot of nice Python libraries that go with it. So most of the code base that I've written for it is all Python based. So the first thing I'll show you is this nice kind of Python GUI that I've got going here. It shows in this plot here is the motor outputs, which is very useful for comparing against the pitch and yaw angles when we're trying to control it. At the moment, all we're going to be controlling for is pitch. So this is pitch here, and yaw is more in this direction. There's some really nice kind of Cartesian kind of what would you call it, mathematics that I've put into it with some matrix transforms and so on to make sure that whatever angle this is at, for example, it always knows what its yaw angle is with respect to the rest of the world. And that's required because the IMU is on the robot itself, so it needs to take into account how it is actually oriented with respect to the rest of the world. And there's a few little modes here for calculating the angles. I've got the still mode, and you've seen here it just jumped, and the reason for that is that in its dynamic mode, when it's actually trying to do some control and that kind of thing, there's a little bit of drift, and that's just from integrating over the gyroscopes. So the still mode then goes, hey, like I know that I'm still, therefore I can use the accelerometers to determine what my actual pitch is. So it kind of takes advantage of some additional knowledge. So you can see that drift now. So I put it back into dynamic mode, and now it's slowly drifting away from what its true angle is, even though the robot's completely still. And if I put it back into that still mode, it would go there again. So you'll see through some of the tests I do, I might put it back into still mode just to zero that. Well, it's kind of zero that angle in a way. Yeah. And then over here, I've kind of got a bunch of PID control stuff as well. So one of the really nice things with the BeagleBone Blue is it comes with this web-based IDE, which lets you more or less interact with it using an IDE quite similar to VS Code. And it lets you do things like pull code from Git and run it and get some nice general output. So this is basically all being served up, over TCP. From the robot itself. So not only is it, sending all this data over and so on, it's also got a little web server effectively that's serving up data as well. So that's really nice to work with. Some other kind of cool features of this robot that I'm quite happy with, this whole chassis is all 3D printed. It uses my Delta 3D printer. It's a Rostock Max for anyone who knows what those are. And then I've also designed these little springs here, which are quite important. So, and you'll see that soon. Basically what I want is if the robot falls for any reason, the control gains are bad, or even if there's an actual software error, then the idea is to basically offload that energy into the springs rather than, having the robot itself smack into the table. I'd prefer not to damage my electronics if I can, because the board itself costs $100 or so, and then there's other parts too. So these are little sacrificial springs that I designed with the 3D printer to help with that. There's also a software cutout, so if the robot goes beyond 5 degrees, it basically just kills the motors down here. to avoid causing any additional damage. And then obviously this ring that I've designed, again 3D printed, is just to keep the robot within a contained space and not let it fall to the floor and cause any real damage to it. Alright, so with that being said, we'll try some control tests. So this is like the first, I've been programming this control and running it in simulation for a couple of days now, but this is really the first time I'm trying to get it into action, and hopefully we can get something a little bit cool out of it. Okay, so it should be now ready to do some control. So I'm just enabling the control over at the GUI there, and let's see what happens. Alright, so the wheels are moving. Okay, didn't go too far that time. Alright, okay, so it's trying to hold position and it falls over. So at the moment it's proportional only. I'm not going to attempt to do any tuning in this video, but you can see it's trying to hold a position. Unfortunately, with these sudden falls, it does have, the control loop on this robot's running at 50 Hertz, but with the sudden falls, it will miss some points in the gyro sampling. So it will lose some accuracy with basically these fast changes in angle. So because of that, coming back to here with the drift, I'll put it back into still mode so that it uses the accelerometers again to calculate the pitch. And you can see just even in that short amount of time we lost about 20 degrees. And so since we're only sampling this at 50 Hertz, and that some of these dynamics, especially if those little springs are going to be outside of that bandwidth, we are going to get a loss in accuracy when we try and integrate over that data, because some of those dynamics won't get captured. Alright. Yeah, let's see if we can get it doing any more control. It seems to be pretty adamant to fall over in that direction at the moment. Okay. Yeah, that seems to be a little bit off. It's saying that that's around the 0, which I don't think is true. Yeah, let's try zeroing that again. Yeah, it just said it was off by 10 degrees from that point, so no wonder we're getting weird control out of it. Alright, one more time. Oh, okay. Alright, let's try turning it around. Maybe it'll do a little run for us. Nope. Okay. This integration really isn't working well for it, I think. We'll try putting it into still again, and then go back to dynamic mode. Okay, no, it fell over. Alright, I think we had more luck in the first run, unfortunately. Alright, well, what I'm hoping is, to play around with this a bit more, and it's got some additional features that I've added to it, like, high-speed logging, where I'm getting that data out at that 50 Hertz rate, and that'll allow me to do some more serious analysis. That's pretty much it for now.
A few moments later.
Ooh. Out for like a second.